Hi guys, today we are going to talk about BCD operation and related instructions. But before we get into that, we need to talk about some background information about BCD. BCD stands for binary coded decimals. Now the next obvious question is why study BCD at all? The reason is computers understand only ones and zeros, and after processing all of the data in ones and zeros, it can display the results in either hex, BCD, and all the different other number systems. Now, BCD, as we can see here, handles numbers between 0 and 9. It means it's the closest to the decimal system, and the decimal system is the system which is the most familiar to the humans. So if we want to be able to read and interpret the results from a computer or results from any computational operation, it will be easier for us to read these results if they are presented to us in BCD. This is why BCD is important. So now there are two terms associated with BCD. We have unpacked BCD and packed BCD. Now, before we get into the different types of BCDs, we have to talk about the difference between hex and BCD because sometimes there is some sort of confusion. Now, it's more illustrative if we use an example. For example, let's say 45 in decimal. Now, the hex representation of 45 is 2D, and 2D in binary, or the 1 and 0 representation of 2D is 00101101. But the BCD representation of 45 in decimal is just representing each of the decimal digit with 4 bit. So there is a difference between BCD and hex, and it's clearly seen here with the example of 45. Now, before we carry on any further, this table shows BCD representation of numbers. We have 0. It's from 0 all the way till 9. We have exactly the same representation for decimals. 0 we have this, 1 we have that, 2 we have 1, 0, 3 we have 0, 0, 0, 0, 0, 1, 1. Exactly as though it was just normal decimal numbers. Now, the difference comes in when these decimal numbers go beyond 9. When the decimal numbers go beyond 9, we have to do like a shift. So after 9, obviously we should have 10, but 10 in BCD is written as 1 and a 0 next to it. 11 is written as 1 and 1 next to it. 12 is written as 1 and 2 next to it, and so on. And then it is just represented in BCD. For example, with 10, you represent 1 with 4 bit and then 0 with 4 bit. For 11, 1 with 4 bit, which is 0011, and the other one with 0001, and so on. So now, let's start talking about the first type of BCD, which is unpacked BCD. Now, in unpacked BCD, the lowest 4 bits represent the BCD number itself, and the rest are zeros. For example, we have 9. 9 represents, since 9 is the main digit itself, is represented as 1001 in binary, and then the other nibble is filled with zeros, and the same goes for 5. Now, unpacked BCDs take 1 bit of memory location. Let's go back to the next slide. Now, if you look at this slide, each of the digits of the unpacked BCD, 9 for example, has 2 nibbles, which is 1 byte of memory location. So every unpacked BCD requires an 8-bit register to contain it. Now, let's look at packed BCDs. In packed BCDs, a byte has 2 BCD numbers, as opposed to unpacked BCDs, as you can see in the example here in 9. 1 BCD number is represented with 8 bits, but for packed BCDs, you will need 2 BCD numbers to fill up 1 byte of memory space, and the lower 4 bits represent the lower digit of the BCD, and the higher 4 bits represent the higher digit of the BCD number. As an example, if you look at 5 and 9 here, this is 5. Since 5 is a higher digit, or the most significant digit of the BCD number, and here it's in the upper 4 bits, or the upper nibble, and 9 is the least significant digit of the BCD number. So it is represented by 1001 in the lower nibble, and the same goes for 9 and 5. Now, again, the same story as we saw in the previous slide. 2 packed BCD numbers take 1 byte of memory location, and packed BCD requires 1n lower or high of an 8-bit register to contain it. We talked about this in the previous slide. So now this figure is very illustrative of what we've mentioned in the previous 4 or 5 slides. Now, on the left side, we have the packed BCD, and on the right side, we have unpacked BCD. Now, actually, what we are trying to accomplish here, we are trying to store the number 81659247 in the memory with packed BCDs using packed BCD analogy, and storing that same number using unpacked BCD in the memory. Now, if you look at this, like we said before, every BCD number fits in 4 bits of memory, or corresponds to a nibble, or can be represented with just a nibble as opposed to unpacked. For example, now we have, and also we have to remember we are talking about the 8086 microprocessor, so we have to take into consideration Little Indian notation. So using Little Indian convention, we have to have 74, 92, 65, and 81 in the memory. So each of these BCD digit is represented with 4 bits. So it takes 2 of the BCD digits to fit in 1 byte of memory. But in unpacked BCDs, each of the BCD digit takes 1 byte of memory. This means to save this number using unpacked, you use half as much space in the memory as you would if you try to save it using unpacked BCDs. So obviously we can conclude from here, as it is said in this next slide, that it is better to save your numbers, or your BCD numbers, with packed BCDs rather than unpacked, because of the memory space it saves. Now the question comes now is, why even have unpacked BCDs at all? And this answer is, while converting from ASCII to BCD, actually packed BCDs, like we said before, the packed BCD has an advantage over unpacked BCD. So generally, all the processing is done with packed BCD. So while converting from ASCII to packed BCDs, the ASCII characters have to be first converted to unpacked BCDs, and then they are converted finally to packed BCDs, and then stored or processed, and then reconverted back to ASCII and then displayed accordingly. It depends on what we are trying to achieve. But the whole idea here is the use of unpacked BCDs is you cannot directly convert ASCII characters to packed BCDs. You have to go through unpacked, and vice. If you have to convert from packed BCDs to ASCII, again you have to unpack it and then do the conversion. Now we are not going to get into the details of how the packing and the unpacking is done between the BCD types of the same number. Not in this presentation, maybe in a future one. Now, let's go to another very important topic concerning BCD, or regarding BCD numbers. We have BCD addition and BCD subtraction. There are 2 instructions that deal specifically. So DA and DAS are the 2 instructions in the 8086 microprocessor that handle BCD addition and BCD subtraction respectively. Now we're going to start with the first one, BCD addition and correction. Now, as we discussed previously, we said for some addition operation in BCD, the result might be incorrect. Now, what do we mean by that? For example, after adding packed BCD numbers, the result may no longer be BCD. For example, let's look at this example here. If we move 17 to AL and we add 28 to AL, we are expecting to have an operation like this. So this represents 1, this is 7, this is 2, this is 8. If we do the corresponding addition, we're going to end up with 3F, and 3F is not a BCD number. So we need some sort of correction mechanism. Normally, adding 17 to 28, we're supposed to have 45 in BCD with a binary representation of this. So how do we do this correction? Now, the programmer must add 6 to the lower digit since the error is found in it. If you look at this previous example, we have a byte, but the error is found in the lower nibble. So we have to add 6 or 011 in binary to that lower nibble. So doing that addition, we'll have 3F hex plus 06. As we can see, a 6 is in the lower nibble. And if we do that addition, we're going to get 45 hex. The same could happen to the upper digit of the BCD addition. So, for example, adding 5 to H to 87H, we get D9 in hexadecimal. Again, we have an error, but this time the error occurred in the higher nibble. So in this case, the programmer has to add 6 to the higher nibble. So adding 6 to the higher nibble, as you can see here, we add 6, 0 hex to D9 hex. So adding this, we get 139 hexadecimal. Now, in the microprocessor, in the 8086 microprocessor, the DAR instruction, like we said earlier on, is responsible for this correction. DAR stands for decimal adjustment for addition. DAR will add 6 to the lower or the higher nibble if required. Otherwise, it leaves the results unaltered. So we can check the function of the DAR from this little code here. Now, let's assume in the data segment we have data 1 defined as data byte 747H, data 2 as 25H, and we are going to keep the sum of it in data 3. So if we move data 1 to AL, data 2 to BL, and then we add both of them, we expect to have an error in the result. Like if we add 747 hex to 25, we are expected to have 72. But doing the addition here, as we can see, it gives us 6C in hexadecimal, which is not true. This is wrong. So the error occurred in the lower nibble here. So we must, in our code, do the addition of 6 to the lower nibble to get 72. But now, the DAR is the instruction that is responsible to automatically correct this mistake. So after doing the addition, after the add instruction, the DAR instruction has to follow. Once the DAR instruction sees 6CH, it will autocorrect itself by adding 06H to this result, and we're going to get 72, which is what we expect to have in the first place. But it's very important to note that the DAR command comes after the add or add with carry command. Otherwise, this will not work. We have to take that into consideration. Now, the summary of the DAR. So to summarize the DAR correction, as you can see here, if after an add or an add with carry instruction, the lower nibble is greater than 9, we have to add 6 to the 4 bits, to its 4 bits. If after an add or an add with carry instruction, the upper nibble is greater than 9, again we have to add 6 to its 4 bit. But in some cases, like in the next example, we will see an extra function of the DAR correction. Now, the DAR correction doesn't only look at the result and check if each of the BCD digits is between 0 and 9. In some cases, it has to check for the auxiliary flag, because only the auxiliary flag can spot the next mistake we're going to have in this example. Now let's look at this example. If we add 2 9 to 1 8, we are supposed to get 4 7, but the BCD addition gives us, for example, here we have a 0 0 1 0 for 2, 1 0 0 1 for 9, 0 0 0 1 for 1, and 1 0 0 0 for 8. If we do the corresponding addition, as you can see, the result here is 4 1, but it's not true. It's supposed to be 4 7, but since there is a carry, an auxiliary carry between this nibble and this one, the auxiliary flag is changed to 1. So the DA instruction checks the auxiliary flag. If it is changed to 1, then it adds 6 to the lower nibble, because the movement was from the lower nibble, the carry was from the lower nibble to the upper nibble. So it has to check for the auxiliary flag and do the necessary addition. Now we're going to talk about BCD subtraction and correction. The same problem or error associated with BCD addition also shows up for BCD subtraction. So during subtraction of packed, be it single or multi-byte operands, the dash is used after the sub or the subtraction with borrow instruction. Now, looking at this example, obviously we are going to have to use SBB, subtraction with borrow, because the subtrahend is less than the subtractor. So if you try to do this, doing this in decimal, we're expecting to have 9, but once you do it in binary, we'll get EFH, which is not a BCD representation. So we have to add 6 to both nibbles because there is an error in both of them. So if we add 6 to both nibbles, we'll get 4 and 5. 4 in the higher nibble, 5 in the lower nibble. Now, we have to add them up. But since during the addition of the 6 to A and 6 to F, we had a carry, we can indicate this with a minus and a minus here. So if we add these two numbers now, we have minus 9, which is the BCD equivalence of the result, which was actually what we were expecting. But in assembly, the DAS does this correction automatically. It's true the DAS operation is a little bit more complex than the DA operation, but assembly does this. In assembly, the DAS operation instruction does this correction automatically, so we don't have to worry about this as long as we put the DAS instruction in the corresponding location in our code. But again, as we mentioned before, the DAS instruction has to come after either the sub or the subtraction with borrow instruction. Now, the summary of the DAS correction. As we mentioned in the DAS correction, if after this operation or this operation the lower nibble is greater than 9, or if, as we saw previously, the auxiliary flag is equal to 1, we have to subtract 6 from the 4-bit. And if after these operations the upper nibble is greater than 9, or the carry flag is equal to 1, we have to subtract 6 from the 4 bits. Now, due to widespread application of BCD number system, a specific directive DT was created. It represents binary numbers from 0 to 10 to the power 20 minus 1. We are not going to talk about this in this presentation. Now, to conclude our presentation, we are going to try to write a code that reads the budget, adds it to the expense, and then stores the value in the balance. Now, to look at this code, we have to use our simulator, and we have our code here. I'm just going to copy this code and I'm going to paste it in the simulator. Yeah, it's done already. So, of course, we start with model small stack 64 because I think 64 will fit for our purpose. In the data segment, we define the budget as, in this case, we want to take an example as simple as it can be, because if it works for a simple example, I mean, it has to work for an even complex one. It's just a bit of further adjustment in the code. Okay, so budget, we define our budget as a word. So we have it here, 5173H. Now, I just use Urge here, although this assembler, this EMU8086 doesn't recognize Urge, but here it's just the name. So I'm going to create space, and this space here is just for us to be able to visualize our results in a better way when we simulate the results, of course. Now we have expense also defined as a word, 3169x, and again we create space again for visual purposes, and then we're going to store the result of this sum in balance. Now in the code segment, now we're going to come back to the reason why these two are found at this location. Now first of all, we give the address of our data segment. Now we're using offset notations in this code because we are trying to accomplish byte by byte addition. So we're going to take this and add with this and store the result, and then take this and add with this too and then store the result. So this is why I'm using offset notation. So we give the offset of budget to SI, we give the offset of expense to BX, and the offset of balance to DI. Now we move whatever is the content of XS. In this case, since it's the first location, so it's going to be 73 to AL, and then we add DL, which is, in this case, we just empty DL first of all. So we're going to come back to this later. We had to empty DL, and I'm going to mention why we had to empty DL and then put it in this location in the code. So DL is empty here. So if I add DL to AL, nothing happens to AL. It is left unchanged. So now we add the content of DX to AL. We check if there is no carry. If there is a carry, we jump, and then we do the following. Now it's going to be better, I think, if I run it with the emulator. Now if I try to emulate the program, we have some errors. Overflow. Where we have to change this to, we had two of these. So if we run the emulator now, okay, now it's running. So sorry about that mistake, it's a bit careless. Okay, so now here we have it. So let's look at our flags, because the flags are very important to illustrate this code. So here we are, and let's load a memory tool. We're going to place it somewhere here, someplace we can see conveniently. We don't care about the DF and this flag. This is the important flag to us. Okay, so now let's go step by step. So we have that DL is 0. We have to pay attention to the flags here. CX is 2 because we are just doing the addition twice. DL is emptied here. As you can see, DL is 0. The next step, we give the address of our data segment. DX is that. We take the offset value, and we go. Now AL just picked up the first value, which is 73. Now I have to update this address here so we can see the results. There we go. So as you can see, now we just gave AX its values. The value of budget, or the content of budget, is in AX now. So we have 73 and 51 according to Little Indian convention. So if we continue, we have that. Now we are trying to add. After this addition, nothing happens to the carry flag. We continue. We do the DAR. Now why did we do the DAR here? We do the DAR here, nothing changes, because if you look at this, we have DC. we have a DC as a result of these two additions. So it isn't in BCD notation. So once we do that, let's see what happens. It's changed to 4-2, but there is a carry, and as we can see, the carry is set here. So we continue, the carry flag is set. As we can see, after doing the carry flag was sent. Since the carry is actually 1, there is a carry. Since there is a carry, we send it back to this. We have to send it back to this. Let me move this a little bit. Since after this here we had a carry, we send the instruction pointer to L0. At L0, DL was empty, so now we're going to save the value of the carry inside of DL. We update DL with 1. So if you update DL with 1 and then we continue again, we do that again, nothing happens to the results. As you can see again, we have 5-1 now. Now it picks the value from DL because we stored it, because in the next nibble we have to consider the carry. This is why we defined the DL on top of this, because after every loop it comes back and reads the offset here. So if you put DL down here, it kind of changes the whole operation of our code. So now it picks 5-1, it adds the content of DL, which makes it 5-2, then it adds it to 3-1. So after the addition we have 8-3, which is what we expect to get at the end of this code. So there we have it. Everything is okay and we are done. So as you can see, we have exactly what we expected and everything works accordingly. Now we expected to have, this is the input, we have the 1, this is the other input, we have these 3 ones, and then yeah, now here we have our expected result, 8347, and of course it's written here following the little Indian convention. So yeah, supposed to have 83 and 47. So yeah, thank you. This is the end of the presentation. Thank you for your time, and you can get